Good afternoon, class. Here's chapter 4, Application of Derivatives, section 4.1, Maximum and Minimum Values. In this chapter, we cover maximum and minimum values, how derivatives affect the shape of a graph, optimization problems, and anti-derivatives, anti-differentiation, integration, the reverse process of differentiation. That's why it's extremely important to be comfortable with differentiation. So here's the definition. Some basic formulas. Definition of E. Again, basic differentiation formulas for the constant, power rule, trigonometric functions, product rule, quotient rule, extended power rule, exponential functions, logs, composite function resulting in the chain rule, everybody. So that's very straightforward. We have seen it many times before. So now I want to continue looking at what everybody knows as delta y versus dy. Delta y is rise along the curve as you go from one point to the next, you connect them. And that is, in this case, this distance, delta y. Whereas dy is the rise along the tangent line. So delta y is equal to bq, dy equals to ab. They are not equal, but delta y can be approximated by dy, where dy has the formula f prime of x dx. Also, if you write the point, if you use the point a comma f of a and write the tangent line, it is known as linearization, everybody. So linearization refers to simply finding the equation of a tangent. And now 4.1 maximum and minimum values definition, critical point, short CP. A critical number point of a function f is a number c such that f prime of x is 0 or f prime of x does not exist, DNE. Here's a simple example. We want to find the critical number for f of x equals x cubed plus 3x squared minus 24x, which means we are going to follow the instruction. Number 1, find f prime of x. So to find f prime of x, we get 3x squared here, 6x here, minus 24. The next step is to set f prime equal to 0. To set f prime equal to 0, I'm going to factor the 3 out. That's a GCF. And that results in 3 times x squared plus 2x minus 8. We can factor, we are looking for 2 numbers. The product must be negative 8. And the sum must be positive 2. We get positive 4 and negative 2. That's how we factor this. That results in 2 answers. One of them is negative 4. One of them is positive 2. If they ask you For pairs, you put them into the original function to find the pair x comma y. For -4, the same thing for +2. The third one, it says where f prime does not exist. F prime is a polynomial with a domain of all real numbers, so it exists everywhere, so we have nothing to worry about. We're going to discuss this concept further in a moment. Let's look at formal definitions for maximum or minimum points on a curve. Local, also known as relative, extreme values. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at a point C in an open interval of A to B in the domain if f of c is less than or equal to f of x for all x values in the open interval. This is the key. On the other hand, a local maximum is the maximum value within some open interval. Local maximum occurs at a point in an open interval of A to B in the domain if f of c is larger than or equal to f of x for all x values in the open interval. So this is less than, this is greater than or equal. And so if you look at both of these, of course, this is a local mean, this is a local max, local mean, local max. In short, peaks and valleys. So peaks, local max, valleys, local mean. Very straightforward. Absolute, also known as global. Extreme value or extrema are either maximum or minimum points on a curve. Absolute minimum occurs at the point C if f of c is less than or equal to f of x for all x values. This was in some open interval. This is in the entire interval, all x values in the domain. Absolute maximum occurs at the point C if f of c is larger than or equal to f of x for all x values in the domain. In other words, if we look at these two cases, local mean, local max, local mean. This local mean is also absolute minimum because no other point has a smaller y coordinate in the entire domain. And that's really the key, all x values. Local max, local mean, local max. This local max is also absolute max. No other point has a y coordinate larger than that. Local or relative extreme values, Fermat's theorem, if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime of C must be 0. So as we look at this graph, peaks and valleys, local max, local mean, local max, local mean, local max. Also absolute max because no other point has a larger y coordinate. Notice if you draw a short tangent line is horizontal, which means f prime must be 0 for those cases. So if f prime exists, f prime must be 0. What about this one? F prime does not exist. Why is that? Sharp corner. So what about the endpoints? If you look at this endpoint, it's nothing. But if you look at this endpoint, assuming the function stops, because sometimes you have arrows meaning continues indefinitely. If it stops here, this is an absolute minimum value of the function. Whereas this one, the endpoints are only absolute, they can't be local. Local is in the interior. But absolute can be in the interior or not. So local extremes in the interior of the function occur where f prime is 0 or f prime is undefined, does not exist. Maxima and minima of a function always occur at critical points. But critical points are not always maximum or minimum values. So a couple of things. So I'm going to recap this. If we are looking at local extrema, it has to be inside the interval of A to B. It can't be the endpoints. The endpoints can only be absolute, if anything. Also, if we happen to have maximum or minimum, okay, those are always where the critical points are. Critical points meaning f prime is either 0 or does not exist. So, but if it's a critical point, meaning it's a point where f prime is 0, it doesn't necessarily mean it's a maximum or minimum. It may or may not be. You have to further investigate. Extreme values can be in the interior or the endpoints of a function. Endpoints can never be a local extreme. So let's look at this good old function y equals x squared, the quadratic function where the domain is all real numbers and that's an open interval. So you have this one as absolute minimum, which is also a local minimum. And if we were to write it, we would write absolute minimum equals 0 at this pair. We don't have an absolute maximum. We don't have a local maximum either. What if we have y equals x squared, the same function, but we have a different interval, a closed interval? The brackets mean the endpoints are included. So this is the portion of a graph that this interval indicates. So we have 0, 0, and 2, 4. See, 2, 4. This is an absolute minimum. This is an absolute maximum, and there is no local extremes. So absolute minimum is 0 at 0, 0. Absolute maximum equals 4 at 2, 4. No local extremes. Endpoints can only be absolute, if anything. We look at the same function. This time, this is half open, half closed, meaning 0 is not included, but 2 is included. So this doesn't produce any minimum. But this one, located at 2, 4, gives us an absolute maximum equals 4 at 2, 4, and of course, no local extremes. Again, let's look at the same function, but this time it's an open interval. That means both ends are out. So we have absolutely nothing. No minimum, no maximum, no local extremes. There is nothing there. Extreme value, also known as closed interval theorem. If f is continuous over a closed interval of a to b, then f has a maximum and minimum value over that interval. So the two restrictions are continuity and closeness. So it has to be a continuous function, and we have to have it close. So what happens? We have an absolute max, we have an absolute mean. By the way, they are both local as well. Local max, local mean, absolute max, absolute mean. So this is absolute max, this is absolute mean, and maximum and minimum at interior points. So somewhere between A and B. Absolute max, absolute mean, max and minimum at endpoints. And endpoints cannot be local. Absolute max, absolute mean, this is also local. So maximum at interior point, minimum at endpoint. This endpoint is nothing, because endpoints must be either absolute max or absolute mean. They are not local. So to find absolute max and minimum values by extreme value or closed interval theorem, and again, the restriction is continuity and closeness. Number one, find the critical points, CPs for short, and evaluate the function at those points, f of CPs. Find the values of the function at the endpoints. In other words, evaluate f of A, evaluate f of B, and finally, the largest value among those is considered the absolute max, and the smallest value is the absolute minimum. Example 2, find the absolute max and minimum values of f on the given interval, where f of x is 1/3 x cubed minus 9x, and the interval is -6 to 0. It's a closed interval. Both endpoints are included. So what do we do? First, before we get to this methodology, everybody, I want to discuss the concept of continuity in general. Recall, this is from algebra. All functions are continuous in their entire domain. So what do we mean by that? Every function we have studied, polynomial functions, rational functions, exponential functions, and otherwise, all of them, logarithmic functions, trigonometric functions, they are continuous in their entire domain, meaning you have to figure out what the domain is. For example, for polynomials, polynomial functions are in the form of f of x equals a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 0. This is the leading term. This is the constant. A sub n is the leading coefficient. A sub n can't be 0. N is a whole number. By whole number, we mean 0, 1, 2 to infinity. The domain for any polynomial of any degree is all real numbers, as an example. So you write the domain, that is where the function is continuous. If you happen to have a different type of function, you have a rational function, you write the domain. Remember, in the case of a rational function, you set the denominator equal to 0 and you exclude that. So the function is continuous in the entire domain, which would be all real numbers, and you exclude those values. So all functions are continuous in their entire domain. The key is to find the domain. So as you look at this function, you notice it's a polynomial of degree 3. Therefore, the domain is all real numbers, and it's continuous from negative to positive infinity, which makes it continuous in the given interval of -6 to 0. So we write f is a polynomial of degree 3, is continuous on the interval of negative to positive infinity, and therefore is continuous over the given interval of -6 to 0. Therefore, now we can move on with the extreme value or closed interval theorem. So you want to find critical points. How do you find it? First, find f prime of x. So what is f prime of x? 1/3 times 3 is 1, x squared minus 9. So x squared minus 9. What is the next step? Set it equal to 0. So to set this equal to 0, obviously it's a squared minus b squared, so x plus 3x minus 3. You have to factor it. When we set this equal to 0, x becomes either -3 or +3. The next one says f prime does not exist. F prime does not exist, doesn't produce any solutions. First of all, f prime is a polynomial itself, so therefore it's defined everywhere, it's continuous everywhere. That's why it doesn't produce everything. Secondly, this notation it's a Greek letter phi, and it refers to an empty set in set theory. Now, can we use -3? Because it's in between, yes. Can we use +3? No, it's not in the in between. Therefore, you just use -3 and you write -3 is an element. So this notation, which looks like an epsilon, it's an element of, again, in set theory, meaning we can use -3. So we are going to go back to the original function, and we are going to evaluate the original function at, so here's the next one, f of a, that means f of -6, f of a b, that means f of 0, f of c sub 1, c sub 2, that means the function at all critical points. Only we have one critical point in the entire domain. So plug in. So here's the original function. F of x is 1/3 x cubed minus 9x. We are going to put -6. 1/3 -6 cubed minus 9 times -6. This one, when you cube it, you get -216. If you multiply this by 1/3, gives you, that means divide by 3, that gives you -72. Negative times negative, positive 54. These two numbers add up to negative 8. Plug in negative 3 and evaluate. This is negative 27. Divided by 3 is negative 9. Negative times negative is plus. Positive 27, they add up to 18. And obviously, if you plug in 0, you get 0. So, step 3, absolute max is the largest value. So absolute max is 18. At this pair, negative 3 comma 18. Absolute mean is the smallest value, negative 18 at this pair. So we write absolute maximum is 18 at negative 3, 18. Absolute minimum is negative 18 at negative 6 comma negative 8. So that's how the writing happens. Example 3, find the absolute maximum and minimum values of f on the given interval. F of x is x plus 3 to the power of 2/3 minus 5, the closed interval of minus 4 to 5. So to use the extreme value or the closed interval theorem, first we want to discuss the continuity. And so what type of function do we have? We are going to rewrite this as cube root of x plus 3 to the second power. When we rewrite it in this format, it becomes obvious that we have a cube root function, which is being raised to the power of 2 and then subtract 5. And this doesn't change the domain of a cube root function. When the index is odd, everybody, there is no restriction. So for example, cube root of 64 is 4. Cube root of negative 64 is negative 4. So the domain is all real numbers. And if the domain is all real numbers, then the function is also continuous in the given interval of negative 4 to 5. So we write f is a cube root function, is continuous on the interval of negative to positive infinity, and is continuous over the interval of the given interval of minus 4 to 5. Therefore, this closed value or extreme value theorem can be used. So what is the first step? F prime of x. Let's find it. To find f prime of x, instead of this, we're going to go back to this one and use the extended power rule. It makes it easier. So it's 2/3 times x plus 3 to the power of 2/3 minus 1, which is negative 1/3, times the derivative of the inside, which is 1, or simply 2/3 x plus 3 to the power of negative 1/3. So to go with the rest of it by setting it equal to 0 and does not exist, we are going to rewrite this so it becomes obvious what we are dealing with. By rewriting it, I mean this has exponent negative 1/3. Throw it to the denominator, make it positive 1/3. So it becomes 2 over 3 times x plus 3 to the power of 1/3. Now you have a fractional format. And I'm going to remind you, a fraction of a to b is 0 when a is 0. So a fraction is 0 when the numerator is 0. A fraction a over b is undefined if b is 0. So in short, you have a fraction. It's equal to 0 if the top is 0. It's undefined if the bottom is 0. In this case, if you set it equal to 0, it gives you no solutions. Why is that? Because the numerator is a number. It doesn't matter if the number is large, small, negative, positive. If you have a number and nothing else, f prime can never ever be 0. So that one is out. What does not exist, a fractional format does not exist if the denominator is 0. So f prime does not exist if you set the denominator equal to 0. Now this should be an easy evaluation. You can simply see, you don't really have to do anything. Right here it tells you if x is -3, everything goes to 0. So can we use -3? Well, look at it. Is it in between? Yes, -3 is an element of -4 to 5. That means it's in between. Therefore, we can use that. Now that we can use it, we go to the next step, find f of a, that means f of -4. Find f of b, that means f of 5. And all the critical points. We have only one. In some cases, we have more than one. F of -3, we have to evaluate all of the above. To do so, we write the function. And it's easier to evaluate it here. So that's why I wrote that one. We are going to plug in everybody. We are going to plug in -4. When we plug in -4 with +3 becomes -1. Cube root of -1 is still -1. Square that and it becomes +1. This is +1. -5, -4. Now, if you plug in -3, clearly this goes away because 0 becomes 0. So -5. What if we plug in 5? 5 and 3 is 8. Cube root of 8 is 2. Square it. You get 4. -5 is -1. All of these numbers are negative, so this one is the largest number. So we are going to, absolute max is the largest value, largest number. So absolute max is -1 at this pair. Absolute mean is the smallest value. The smallest value is -5 at this pair. And we write absolute maximum is -1 at 5, -1. Absolute minimum is -5 at -3, -5. Again, I want to emphasize, this is the way I like to write it. As you do your homework or exam questions, write it the way as they ask you. Sometimes they just want the pair, sometimes they just want the absolute max, and then add the x coordinate as they wish, so you get full credit for that.